Alright, last video of the year, woohoo! So the last topic we're going to look at is what's called a diffraction grating, and then we're going to look at an application called a spectrometer. And diffraction gratings are essentially not single or double slits, but a whole bunch of slits. So just like that slide I showed you in class, that double slit slide, instead of having two real thin slits in the middle, you're just going to have slits all along this sucker. And it acts a whole lot like a double slit, but what happens is the more slits you get, the more narrow and defined the bright spots become. So instead of having bright locations that are kind of broad like this, where it's real bright and then it kind of tapers off and gets dim, you get really bright in one location, and then over here it's like no light at all. So you get real distinct bright fringes. And so these are particularly useful for making measurements, because it's easy to have an exact location as opposed to some kind of spread out location like these waves up here. So here's how they work. If you've got a bunch of different slits and light is coming through at a given angle, we're assuming that light diffracts through these slits widely, so these slits are narrow enough that you get a lot of diffraction, so that the light from every slit is interacting with every other slit. And so what we want here is, if we are at such an angle that the difference in the distance for adjacent rays, this difference here, delta L, which again is going to be d sine theta, as we've seen a bunch of times, if this is equal to a multiple of the wavelength, again like we had with double slit diffraction, then we're going to get constructive interference. Let me grab my pen here. So if this equals m lambda, then we are going to get a bright spot. And we still call the separation between slits d, only now it's, well, a lot of times we aren't given d, we're told how many lines per centimeter there are. So if you've got, I don't know, 300 lines per centimeter, and you want to know the slit spacing, you have to invert that, right? So d, the separation between one line, would be 1 over 300, and that would be centimeters per line. So we're going to have to deal with flipping that information a bit, because usually they give it to you in this form, and you need it in this form in order to plug it into our equation here, the d sine theta thing, right? Okay, so just looking at, there's the equation for you all nice and neat. Move the d over here, and again you plug in 0, 1, 2, 3. So you do get a bright fringe right in the middle with m equals 0, and then you get fringes on either side corresponding to m equals 1 and m equals 2. What this is showing here is if you have two frequencies of light that are both going through your diffraction grating, then you get a series of lines, and they will spread out differently if they're different wavelengths. And you get a pattern that looks like this. If you have white light, so all the colors of the rainbow, you're going to get bright lines for each of the colors, and so it will spread out in this nice spectrum rainbow effect here. You'll get rainbows at each of the locations of the order of the fringes, right? The first order fringe, second order fringe. Now with diffraction gratings, you get really bright defined fringes and then really dark in between. And each successive fringe is quite a bit dimmer than the first. So this first fringe here is usually what you're going to be measuring and looking at. It's going to be nice and bright and well defined. And the device that we use to actually make these measurements is called a spectrometer, and the science of using spectrometers to measure these things is spectroscopy. And so what you have is you'll have your source of light here, and you're interested in measuring the wavelength of this light, and you'll send it through a slit or something to get it collimated, not a really narrow slit because you don't want it diffracting, but you don't want the light that was heading out in all directions, right? So if you got a source that's shooting out light in all directions, you want these rays to be traveling parallel. Okay, and then you bounce that off the diffraction or through the diffraction grating. And then you can, this scope here is usually movable, so you can move it around until you get the best view of the bright fringe, and then there will be some scale on the outside or something that you can read the angle off of, and you can get incredibly precise measurements of wavelengths of light when you do this. Oh, one other thing I forgot to mention. So I drew that little picture earlier of the diffraction grating where you cut slits into it. A lot of times, rather than putting holes, actual slits, what they'll do, this isn't going to look any different, but a lot of times they'll use a mirror instead, just because it's easier to manufacture. And so they'll have a regular mirrored surface, and then they will scrape lines into the mirror. And so when you reflect it off this, the reflected regions are like the openings on your slits here. And so you can make a spectrometer with a mirror as well, and then you just have your telescope. You know, if this is your mirror, it's going to be bouncing off over here, and then you put your scope over there. Still works. There's a variety of different designs for these things, but these have a lot of uses in science in a variety of areas, particularly in astronomy, because each different element is going to give off a distinct signature of lines, of diffraction lines, when the light from a glowing element is passed through a diffraction grating. So, for instance, if you had a tube full of helium gas and you ran some current through that, so it lit up, and you took that light and passed it into a diffraction grating, you would get these distinct lines here. And this is like a signature, it's like a fingerprint. Whenever you see these particular lines with this particular spacing, you know that that's got to be helium. Hydrogen gas is going to give you this, and so forth. And this is how we know about the chemical composition of stars and distant planets and whatnot. It's not like we've got a telescope and we can zoom in and say, oh, look, there's water in the atmosphere. But we look at the light coming from the atmospheres of those things, and we get these distinct fingerprints, and we know, oh, that's got to have water in the atmosphere of that star. This is why we know that the sun is made of hydrogen and helium. We haven't actually gone and scooped up a sample of that, but we analyze the light coming from those things. We analyze light from supernovae, from all kinds of things, and this is how we know what elements are out there. So this is a huge tool for astronomers. And the reason why each one has a distinct signature has to do with the transitions that are possible and the energy levels of the electrons, if you remember your chemistry. So electrons, if you get hit with a photon, you can get excited, and then it de-excites and gives off a photon. And these are quantized energy levels, and so there's only certain transitions that are allowed that correspond to certain energies. And these energy levels differ from atom to atom, and so that's why each atom has distinct signatures. Here are some of the transitions possible in hydrogen, the simplest element. So if you go from energy level 1 to 2, you're going to give off a 122 nanometer photon. If you go from 1 to 3, you'll give off 103, and so forth. So you have all these transitions, and different people identified these different series. There's the Lyman series, Balmer, and Paschen series. And Balmer was actually a teacher, so hooray for teachers. Okay, I think that's about it. So, on to the calculations.